Hello everyone, today I'm going to show you how to create a simple crash test on a square tube using Abaqus 6.13. In order to do this crash test, we have to go through these modules over here in the software. Part module, property, assembly, step, interaction, load, mesh, and then we create a job and then we run it to obtain the results from this crash test. So our part is a square tube of the dimension of 80 millimeters times 80 millimeters. So to start with this process, first we have to go to the part module and then we create our part, which is the square tube and then the two crushing plates. So we create our first part, which is the tube. Let's call it square tube. The modeling space is 3D. The type of the tube is deformable. The base feature, it's solid. It's shell, and then the type is extrusion. Here's our drawing space. The easiest way to go about drawing this tube is to draw the corners of the tube. We select this create isolated points. We go here. We define our x and y points, which represent the corners. And in our case it's 80 times 80, so we will go with 38, enter, and then 38, negative 38, and then negative 38, negative 38, negative 38, 38, enter. We zoom back. These are the points. We connect these points by selecting the line over here. And we got the cross section. Now we have the cross section of the tube. We click escape and then done. Then we select the length of the depth of our extrusion, which is the length of the tube, which is 350 millimeter, and then we click OK. And here we're done with the tube. This is the first part, which is the tube. Now in this crash test we will need two plates, one to fix here, right here, and the other plate is to be moved here to create the crash test. So we create two other parts. Let's call it top plate, and this top plate is the one which will be moving. And since it's a plate, we don't need it to be deformable, so we'll select here discrete rigid. And as for the shape, we select shell also, but the type we selected to be planar. Continue. Same way as we did with the tube, we go with the isolated points, and then we enter the XY coordinates here. We need to make the plate bigger than the tube cross section, so we will go with 45, 45, enter, 45, negative 45, negative 45, negative 45, negative 45, 45, enter. We zoom back. Here are the points that we have created. We connect them. And then escape, and then done. We have our plate. Now we need to create a reference point on that plate. I will explain why we did that later. We create a reference point and then we write here 0, 0, 0, which is the origin of our drawing space. It will show here. So now we need to create another part, which is the lower plate, but since we have the upper plate already, we can copy it since they are the same. Copy top plate, name it lower plate. Now we have three parts here. You can see lower plate, top plate, and square tube. Both top plate and lower plate have reference points. I suggest that we rename each point. So here lower plate, it's named RP, reference point, rename. Let's call it lower since it's on the lower plate. We do the same thing to the upper plate, rename. let's call it upper or top, it's easier. Okay, and now as you can see we are done with the part module over here. So now we need to move to the next module, which is the property module. In this module we need to define our materials, and the material of our plate is aluminum, and we need to create this material. So we select square tube, we go here, material manager. This material is already there, so you will not find it. Now we create our material, let's call it aluminum. So the first thing that we need to define for this material is the density of the material. We click on density, and then we write our materials parameter, which is the mass density, and I have the properties over here. The mass density is 2.7 e to the power negative 9 ton per millimeter cube. And be careful that we need to use certain units when dealing with Abaqus, because it doesn't understand, it doesn't define your units alone. So since we drew the tube in millimeter, we need to stick with this unit, and the unit that goes with millimeter in terms of density is ton per millimeter cube. So I will take this value over here, and I will copy it here. This is our mass density. And now as for the elastic behavior, over here I created an elastic behavior. We need the Young's modulus, and the Poisson's ratio, and I have it over here for this certain material, 68,210 megapascal. Copy it. And as for the Poisson's ratio, it's 0.3. Now we still have to define the plastic behavior. We go to mechanical, plastic, and then we enter the yield stress value and the plastic strain, and I have them in this table over here. I will not waste time, I will copy them, and you can pause the video and copy and just copy them as well. Paste. That's it. We have defined our material. Select OK. Now we have to assign this material to this tube. In order to do that, we create a section. We go here to section manager, create. Our part we created to be shell, so we select shell over here. Let's write tube as the section name, shell, homogeneous, and then continue. Now for the shell thickness, we said our tube has to be 80 times 80, and you notice that when I drew the tube, I select the corner point side are 38 times 38, which is less than 80, which is 76. That's why here in the section assignment I will assign the shell thickness to be 2 millimeter, and I will tell you why. Okay. Sorry, here, yeah, the material is aluminum. I'm just showing you that. We just created that, so we selected here to be aluminum. Okay. And now we go to assign section assignment manager. We create, and then we select the tube, and then done. And then here, edit section assignment. The shell offset, we will select it to be top surface, and then OK. Now the aluminum material is assigned to this certain tube. Now as for the top and lower plate, the lower plate no material is needed for both of the plates, but for the top plate we need to assign a mass. So we go here to part, and then we select top plate, and then we go to special, inertia, create, point mass inertia, continue. We select the reference point, done, and then we enter the mass of the plate. Let's let's enter 0.275, which is 0.275 ton, 275 kilograms, and then OK. Now we are done with assigning the mass to the top plate, and we are done with the property module. We move to the assembly module, where we have to assemble our crash test setup. We go here, create instance, and we double click the lower plate and the square tube, and then cancel. We rotate the view. Now we have to move this lower plate over here, from here to here. In order to do that, we go here, translate instance. We select the top plate, the lower plate, and then done. And then it's from that position. So just click enter, and then the other position is 350 in the Z direction. So we write here 350, and we keep the 2 zeros for X and Y there, and then enter. The plate moved. Now we have to go and create another instance to insert our top plate. Create instance, top plate, double click, that's it. Now we have our setup over here assembled, and everything is good. Now we move to the step module. And in the step module, you have to define your step time and the points required from this crash test as data points. So we go to step manager. We create a step, let's call it crash. It's not static, it's dynamic explicit. So we select dynamic explicit, continue, and let's select the time period to be 0.06. You can change it later, but we chose this time period in order to assure the crash is complete. OK, dismiss. Now we go to output, field output, manager, edit, and here we select 100 points. 100 intervals mean 100 points of data, which will make our results accurate. We click OK, and we are done with the step module. Now we move to interaction. Now for the interaction, we need to fix the tube with this lower plate, and to do that we go to constraint manager, create a tie constraint, continue, choose the master type surface. We select this surface, the lower plate, and then done. And then I will rotate the view for you here to understand what is the meaning of brown and purple over here. They're asking about the surface color, which one you need to, which side of the surface you need it to be connected with the tube. Of course, it's the purple one, so we select purple. And then the slave type, we have to select the tube surface, the tube edge over here. I will rotate the view, and then we select these lines over here. Click on the first one, and then shift, click on shift, and then click on this edge also. Keep pressing shift, and then click on this one, and then click on this one, and then done. We have created the tie contact. Here we click OK, and we're done with this thing. We have also to define a contact algorithm for the whole crash test over here. And in order to do that, we go to contact interaction manager, create. We select general contact, but here we have to change the step to initial. General contact, continue, and here we create interaction property, contact, continue, then tangential behavior, penalty, in order to account for the friction between all the surfaces that we have. Friction coefficient 0.2. Okay, we select what we have created and then click on OK, and we're done with the contact between all of the parts that we have, this mess. Now we move to the load module, where we have to create our boundary conditions. And as for our boundary conditions, we will have to prevent this top plate from moving in any other direction during the crash. So we will constrain it to the X and Y direction and only allow it to move in the Z direction. And in order to do that, we go here, boundary condition manager, create. We go to initial, mechanical, and displacement rotation. Let's call it let's keep it as it is, BC1. And then we continue. We select this reference point. That's why we created the reference point, to assign the boundary conditions to one. We select it and then done. These are the directions of the motion. U1 means X, U2 means Y, U3 means Z. So we select all of the other directions that we don't need the plate to move in. So we will let the Z direction free, so the plate can only move in this direction. Okay. We create another boundary condition for the fixation for the fixation of the lower plate, BC2 initial. Symmetry, we select this one, symmetry, anti-symmetry, anti-symmetry, and encastre. Continue. We select this reference point lower, done, and then we click on encastre to fix the plate. Okay. Now the last boundary condition that we have, we need to do is the velocity or the speed of the plate during the crash. And the speed of the plate during the crash is 15.6 meters per second. You can change it, but this is the one that I have. So we go to do that, we go to create predefined field, initial, mechanical, velocity, continue. We select the top plate reference point, done. And V3, of course it's V3 since it's moving in the Z direction, we need it to move in the Z direction. The plate is in the Z direction, 15.6, which means 15,600 millimeter per second. And then OK. The reason why we selected predefined field is to assure that the tube will leave the top plate will leave the tube after the crash is finished. If we could have done the speed boundary condition from the boundary condition manager over here, but this will not assure that the plate will leave the tube after the crash is done. Now, after we are done with the load module, we move to the mesh module. And in the mesh module, we need to mesh the tube and the top plates. And to do that, we click on seed part. You will have this message: dependent part instances could not be edited or assigned mesh attributes. So when you see this message, you go directly to assembly here on the left, instances, and you make your instances independent. Make independent. You select them all, and to select them all, you click on one, and then you press Control and click on the other one. Click on the third one, and then make independent. Once you make them independent, you will see that the color is changed in the mesh module, and now you can mesh them. So as I said, you go to seed part, you select your part, which is the tube, and then done. Before that, we need to select the element of the mesh. Sorry, the type of the element of the mesh. And to do that, we go to Tools, Mesh, and then Element Type. Then we select our tube, and then done. And since it's a shell element, it's a shell tube, we have to select the shell element, and it's defined here already, so it's for R, and then OK, done. Now we seed the part. We go here, we select the tube, then we click on done, and then here we select the global size of the mesh. Let's choose it to be 5 I guess 5 is good. Let's select, yeah, 5 is good. Apply. Okay, done. And then we go to mesh part instance. Over here we select mesh part instance, we select the tube, and then we click on done. We have our mesh here, done. Now we need to mesh the top and lower plate, and the size of the mesh for both of the plates, it doesn't matter because they will not affect the crash test a lot, the results on the crash test. So we select here the lower plate and then press shift, we select the top plate, both are selected together, and then done. 9 is good, let's make it 10, and then apply. Okay, done. And then we do this, we do the same thing that we did to the tube. We go to mesh part, we select the lower plate, press shift, select the top plate, done, and we have meshed the whole setup, and we're done with the mesh module. Now we go to the job module, where we have to create the job of the crash test. Job manager, create, that's called crash tutorial 1. Continue. Okay. Here's our job, and now we can submit this job and wait for the results. Submit. Of course it will take a while, so I will be back again with you once this job is done. So after a while of submitting the job, the status here should be completed, but I have killed this job to save time. I've killed it before it's done, but I assured that the crashes took place. And to see that, we go to results, and then we go here, and we can play with the steps. As you can see, the top plate is moving and crushing the tube, and by this we can end this tutorial. And in the next tutorial I will show you how to obtain the data points from this crash test and analyze them to obtain the energy absorption and the maximum load, and all the other data that are related to this crash test. Thank you for watching.